Imagine a future where neurological disorders are not just managed, but truly treated, where lost functions are restored and the brain's mysteries are unlocked. This future is being built today, powered by groundbreaking advancements in biocompatible neural implants. These tiny, sophisticated devices are revolutionizing neuroscience and neurology, offering unprecedented avenues for diagnosis, monitoring, and therapeutic intervention. But their success hinges on one critical factor: biocompatibility. Without it, even the most advanced implant is destined to fail, causing more harm than good. Biocompatibility is far more than just the absence of adverse reactions. It's the harmonious integration of a foreign material within a living system. For neural implants, this means the device must not only avoid causing inflammation or tissue damage, but also maintain its functionality and structural integrity over extended periods, ideally for a patient's lifetime. This intricate dance between implant and host tissue dictates the device's efficacy, longevity, and, most importantly, the patient's quality of life. It's a fundamental principle that underpins all successful neuroprosthetics and brain-computer interfaces. A truly biocompatible implant fosters a stable, functional interface with neural tissue. This allows for reliable signal recording or stimulation, crucial for applications ranging from deep brain stimulation for Parkinson's disease to prosthetic limb control. Conversely, a non-biocompatible implant can trigger a cascade of detrimental events, leading to device encapsulation, signal degradation, and even severe neurological complications. For scientists, engineers, and researchers, understanding and achieving this delicate balance is paramount. Despite the rapid pace of innovation, achieving true biocompatibility in neural implants remains a formidable challenge. The brain is an exquisitely sensitive organ, and introducing any foreign object triggers a complex biological response. Overcoming these hurdles requires a multidisciplinary approach, blending material science, neurobiology, and advanced engineering. Each challenge presents a unique puzzle for researchers to solve. The most immediate and persistent challenge is the foreign body response, FBR. When an implant is introduced, the brain's immune cells, primarily microglia and astrocytes, perceive it as an intruder. This triggers an inflammatory cascade, leading to glial scarring and the formation of a dense fibrous capsule around the implant. This encapsulation physically isolates the device, increasing the impedance of recording electrodes and hindering effective signal transmission or stimulation. This chronic inflammation can also lead to neuronal cell death in the vicinity of the implant, further compromising its therapeutic potential. Understanding the molecular pathways involved in FBR and developing strategies to modulate or suppress this response is a critical area of ongoing research. Scientists are exploring various biological and material-based interventions to mitigate this inherent defense mechanism. The brain is remarkably soft, with a Young's modulus in the kilopascal range. Most traditional implant materials, such as metals and ceramics, are orders of magnitude stiffer, possessing Young's moduli in the gigapascal range. This significant mechanical mismatch creates chronic stress at the implant tissue interface. Micromotion, even at a cellular level, can lead to continuous tissue irritation and inflammation. This mechanical incompatibility contributes significantly to the FBR and can cause physical damage to delicate neural tissue. Engineers are actively developing ultra-flexible and compliant materials that more closely mimic the brain's mechanical properties. This involves innovative designs and novel material compositions to reduce stress concentrations and promote a more harmonious mechanical integration. Any invasive medical device carries an inherent risk of infection, and neural implants are no exception. The implant can act as a conduit for bacterial colonization, leading to severe, often life-threatening, central nervous system infections. Biofilm formation on the implant surface makes these infections particularly challenging to treat, as bacteria within biofilms are highly resistant to antibiotics. Preventing infection requires meticulous surgical techniques, sterile environments, and, increasingly, the development of antimicrobial implant surfaces. Researchers are exploring coatings that release antimicrobial agents or possess inherent antibacterial properties. This is a critical area for patient safety and long-term implant success. Neural implants are designed for long-term use, often decades. However, the harsh biological environment of the brain, with its fluctuating pH, enzymatic activity, and oxidative stress, can cause materials to degrade over time. This degradation can lead to a loss of mechanical integrity, electrical functionality, and the release of potentially toxic degradation byproducts into the surrounding tissue. Understanding the long-term stability of biomaterials in vivo is crucial. Researchers must meticulously characterize degradation pathways and rates for all components of an implant. This includes not only the primary structural materials, but also coatings, adhesives, and even electrode materials. Ensuring material stability is key to maintaining consistent performance and patient safety over the implant's lifespan. Beyond physical and chemical degradation, neural implants, especially those involving electrical stimulation or recording, face challenges related to electrochemical stability. The continuous flow of electrical current can induce electrochemical reactions at the electrode-tissue interface. These reactions can lead to electrode corrosion, material dissolution, and the generation of reactive oxygen species or other neurotoxic byproducts. Maintaining a stable and safe electrochemical interface is paramount for long-term neural modulation and recording. This involves careful selection of electrode materials, optimization of stimulation parameters, and the development of coatings that enhance charge transfer efficiency while minimizing adverse reactions. This area requires a deep understanding of electrochemistry and neurophysiology. The choice of biomaterial is foundational to an implant's success. Each class of material offers unique advantages and disadvantages, and ongoing research is focused on optimizing their properties for neural applications. The quest for the ideal biomaterial is a continuous journey, pushing the boundaries of material science. Metals like platinum iridium, PTIR, gold, and titanium have been widely used in neural implants due to their excellent electrical conductivity, mechanical strength, and relative inertness. PTIR in particular is favored for electrodes due to its high charge injection capacity and corrosion resistance. Titanium is often used for implant casings due to its strength and established biocompatibility in other medical devices. However, metals are prone to corrosion in the biological environment, leading to the release of potentially toxic ions. Their high stiffness also contributes significantly to mechanical mismatch. Researchers are exploring surface modifications, such as thin-film coatings or nanostructuring, to enhance their corrosion resistance and improve their interface with the neural tissue, mitigating some of these drawbacks. Ceramics like alumina, Al2O3, and zirconia, ZrO2, offer exceptional biocompatibility, chemical inertness, and corrosion resistance. They are often used for implant substrates or insulating layers due to their excellent dielectric properties. Silicon carbide, SiC, is another emerging ceramic with promising properties for neural interfaces due to its high strength and biocompatibility. While highly stable, ceramics are inherently brittle, making them susceptible to fracture under mechanical stress. Their high stiffness also presents a significant mechanical mismatch with brain tissue. Fabrication of complex, micro-scale ceramic structures for neural interfaces can also be challenging, limiting their widespread application in highly flexible devices. Polymers represent a highly versatile class of materials for neural implants, offering unparalleled flexibility, ease of fabrication, and tunable mechanical properties. Polyurethane, Known for its excellent biocompatibility and flexibility, polyurethane is often used in chronic implants. However, some formulations can be susceptible to oxidative degradation in vivo, limiting their long-term stability. Polyamide. A robust polymer with excellent electrical insulation properties and mechanical strength, polyamide is widely used as a substrate for flexible electrode arrays. While mechanically strong, it can still be significantly stiffer than brain tissue. Paralysis. This conformal, biocompatible polymer is often used as a thin film coating to encapsulate and insulate neural devices. It provides an excellent moisture and chemical barrier, enhancing device longevity. However, its mechanical properties are limited, and it's typically used as a coating rather than a primary structural material. Benzocyclobutene, BCB. An increasingly popular polymer, BCB offers a unique combination of flexibility, excellent dielectric properties, low moisture absorption, and good biocompatibility. Its ease of processing and patterning makes it highly attractive for fabricating high-density, flexible neural probes. BCB's tunable mechanical properties allow for the creation of devices that more closely match the brain's compliance, reducing mechanical stress. The ability to tailor the properties of polymers through synthesis and processing makes them ideal candidates for next-generation neural implants. Researchers are developing novel biodegradable polymers that can dissolve after their therapeutic purpose is served, minimizing long-term foreign body response. Even with the best biomaterials, the surface properties of an implant are critical in determining its interaction with biological tissue. Surface modification techniques are powerful tools to enhance biocompatibility, promote desired cellular responses, and mitigate adverse reactions. These techniques allow engineers to fine-tune the implant's interface without altering the bulk's material properties. Applying a thin, biocompatible coating to an implant surface can significantly improve its performance. Materials like paralysis, polyamide, or even hydrogels can act as protective barriers, reducing direct contact between the bulk implant material and tissue. These coatings can also be engineered to reduce protein adsorption, minimize inflammation, or even release therapeutic agents. For example, drug-eluting coatings can deliver anti-inflammatory drugs directly to the implant site, suppressing the FBR, modifying the topography of the implant surface through techniques like laser ablation or chemical etching can influence cellular adhesion and tissue integration. Controlled surface roughening or texturing can promote the growth of desired cell types, such as neurons, while discouraging the formation of glial scar tissue. Nanoscale features, in particular, have shown promise in guiding cell behavior and improving biointegration. This approach leverages the body's natural tendency to interact with specific surface topographies. Chemical modification involves altering the surface chemistry of the implant to present specific molecules or functional groups. This can include grafting polymers, immobilizing biomolecules, e.g., growth factors, cell adhesion peptides, or creating zwitterionic surfaces that resist protein adsorption. These modifications can actively modulate the immune response, promote neuronal survival and outgrowth, or reduce the risk of bacterial colonization. This highly targeted approach allows for precise control over the biological interactions at the implant interface. While material selection and surface modification are paramount, other often overlooked factors significantly influence the overall biocompatibility and success of neural implants. A holistic view is essential for accurate research and effective clinical translation. The in vivo environment is dynamic and complex. The physiological state of the cells and tissues surrounding the implant, their metabolic activity, oxygenation levels, and inflammatory status can profoundly impact the histological accuracy and the long-term performance of the device. For instance, a brain region experiencing ischemia or pre-existing inflammation will respond differently to an implant than healthy tissue. Researchers must account for these variables in their experimental designs and interpretations.